Hi, and welcome back to this video series for the book Dynamic Thinking, a Primer on Dynamic Field Theory. In this video, I'm going to go through the exercise 1, that's the first exercise of the first chapter, and this exercise is subdivided into 3 parts. And there are 3 tasks concerning tracking, the relaxation time, and the stability of a dynamical system. So they all have to do with a single dynamic activation variable with input, and all 3 tasks use the same simulator. In fact, it's the same simulator that I've already showed in the first video where I explained how to install Cosivina. So we're going to open that simulator. Now remember from the other video, we've created a folder Cosivina. And in there is an examples folder, and in there are all the simulators that you need for the exercises of the book. So for this exercise, actually for all 3 tasks, we use the simulator called launcher2neuron-simulator.m. We click this file, and then we run it, and this is the simulator. Now let's have a look at what this is. This is a simulation of 2 dynamical systems. The equations are printed in the book. Have a look at them if you like, and try to understand what each term in the equation actually does, and how it corresponds to these controls and to the elements that you see here in the plots. I'm going to explain what all these things are. Let's start with the plots that you see here. So we have 2 dynamical systems. The activation variables are called U1, like this, and U2. And you can see that we have 5 plots. These 2 up here are for U1, for the first dynamical system. These 2 down here are for the second one, for U2. And this plot here is basically a combination of both. It shows you the state of both at the same time. We'll cover this in a second. Let's maybe start with this plot here. This is called a phase plot, where we plot the rate of change of the system. This would be U dot over the activation itself, so over U. Okay. So in the equation, this U dot would be on the left side, and the U itself would be on the right side. And you can see that there's a function here where I can read off the rate of change for different activation variables, activation values. Okay, so there's a line here with a downward slope, which actually is important. The 0 crossing here is a fixed point, and it's marked, you can't see that right now, it's marked with a little square, because this point, this fixed point, is an attractor of the system. The red dot that covers the square is the current activation value that this system has. Okay, so this dynamical system is currently at a value of around -5. You can read this off here. Okay, and the rate of change at this value of -5 is 0. You can read this off here. So that means that at the moment the rate of change is 0, so this is why it's not doing anything, it's not moving anywhere. Okay, maybe let's have a look at this plot. This is a phase plot, and this is a trajectory plot or a time plot, where you have the activation, what we saw here, the activation of the system plotted over time. And if you look at the axis down here, you'll have 0 time, so this is the moment right now at the very right, and then these negative times. This This is a notation saying that this here, what you see here, this line, this is the history of the system. Okay, and in a second you'll see that values that start here, they kind of move to the left. So here we can again see that the current state of the system, U1, is at -5, the same that we saw here. And the rate of change isn't plotted directly, but you can see that it's not moving, right? So the rate of change must be 0. We have exactly the same type of plots down here for the second activation variable, U2. So there's a phase plot here and a trajectory plot here. What you can see here on the left is a plot of the activation of the second variable plotted over the activation of the first. Okay, so what we can see is that both activation variables are at -5. So for a coupled system like this, which interacts between these two activation variables, this plot is useful to show the state of the entire system. Okay, so you could, for instance, see movement in a circle here, depending on if you set this up right. You could do circles and other shapes. Okay, so these are the plots. Up here we have controls for these systems. So these sliders here control different parameters of the first dynamical system, while these sliders control the same parameters but for the second dynamical system. You can see the subscripts here. These are all with 1 corresponding to this one, these with 2. Now the tricky thing is probably, if you look at the equation, to try to figure out what all these terms are and how they correspond to these sliders, right? So let's just have a look at what each of these sliders do. So this h variable, h1, is the resting level of this dynamical system. Okay, this is set to -5. If I change this, let's say to -6, you'll see that it has an effect on the system here. And what it does is it shifts this system downward here, shifting the attractor to the left. And if I add resting level, it does the opposite. Okay, shifting it back to 5. This is the resting level. The second one is the noise variance. So Q is currently at 0. This is why it doesn't have any noise. If I add something here, you can see that it starts wobbling around a little bit. Now this is heavy noise. You can see that it's really noisy, but it's always oscillating around around this resting level that we set before. It's always coming back sort of to -5, and this is a property of the system. It has an attractor at -5 which pulls it in. If the noise pushes it to one of these two directions, the attractor pulls it back to this position here. I'll lower this back down to like a smaller value. Now, let's maybe skip these two and go to the S variable. The S variable is the input of the system. So right now it's at 0, and we can add input like this. It has basically the same effect as changing the resting level, but we see the input as something that can come from outside of the system, while the resting level is something that is inherent in the system. Okay, so we can add input and remove input here. Now back to these C variables. C11 is the variable that controls the self-excitation of the system. So how much the activation of this dynamical system has an influence on itself. If I change this, you'll see that there's a bump created here that wasn't there before. And it has a characteristic shape of like a sigmoid added to this downward slope. And this is because the output function of this dynamical system is a sigmoid function. Okay. Now this creates a certain characteristic that we'll have a look at in the future, but for now, just remember that this is the self-excitation. There's another slider here, C12, which determines the interaction between these two systems. The tricky thing here is to remember the direction of this interaction. So in the book and also throughout these simulators, we decided to go with a mathematical notation that's a bit counterintuitive. C12 is the interaction strength that is targeted at 1. So it comes from 2, goes to 1. Down here we have the same thing, but C21 comes from 1, goes to 2. Okay, so if I do something here, it doesn't have an effect right now because this dynamical system is currently not active. We can change that. Let's activate this node by pushing it to a positive level. Now it's positive, right? It has an activation value of 5. Now it's active, it's producing output of around 1. And that can have an effect on this node. But now we'll have to change this slider. This is the interaction that goes from 1 to 2. So if we change this, if we add it here, you can see that this is now pushing this dynamical system up. If I remove the input of this node, it'll also have an effect on this node down here. Okay, this turns off and then this goes down as well. Okay, so we understand these controls. Now there are a few buttons down here which I can cover as well. So the pause button does exactly what you think. It pauses the simulation. You can pause to have a look at something, then you can unpause it to keep going again. Then there's a reset button, which doesn't seem to do anything if you look at it, but it does have an effect. It resets the dynamical system. Let's say if I add an input of 9, maybe I'll get rid of this interaction for a second. Also get rid of the self-excitation. So if I add the input, then this is now the system is following the input. If I reset it, it starts from the resting level back up. And you can use the reset to, for instance, start two dynamical systems with the same parameters. We'll actually use this in the future. So resetting kind of does this, okay, without resetting the parameters themselves. Then there is a save a load button for different configuration files. You can save configurations and load them. There's a quit button, which quits the simulation. In here, there's another parameters button. Let's click on that, and you can see that there are even more parameters that you can tune. Up here is a drop-down list for the different nodes that you can check out. So this is for node 1, for node 2, stimulus S1 and stimulus S2. So for node 1, for instance, there's the tau value, which determines the relaxation time, and we'll play with this in a second. This is set to a value. If you want to change this, you can type in a value here, for instance, multiply this by 10, and then you can click apply down here, and it has an effect on the system, as you see. Let's revert this back. And there are some other parameters that you can change. Okay, we'll go into this later. Okay, so I think now we understand what the simulator can do and kind of how it works. So let's have a look at this exercise 1. And to do that, I'll quit the simulation and restart it, just so that all the parameters are back to where they were. Okay, so we're now at a state where we have two dynamical systems. Both are at -5. There's no noise here, no interaction, no self-excitation. Okay, so now the first task is this is exercise 1, task A, tracking. And I'll read this and then see what we'll have to do. Explore how the activation variable tracks a shifting input. Use the S1 slider to set the input parameter to different values and observe how the zero crossing of the phase plot of U1 is shifted around. So let's look at this. Explore how the activation variable tracks a shifting input. We actually saw that a little bit, but let's do this right now. Use the S1 slider, that's up here, to set the input parameter to different values. So we can do this, right? I'll pause it for a second. And observe how the zero crossing of the phase plot of U1, that's the phase plot is this. The zero crossing is where this line goes through zero, and observe how the zero crossing shifts around. Okay, so let's see. If I remove the input, you can see that the zero crossing is here. If I shift it here, you'll see that there's zero crossing moves to the right. Okay. Now you may get the impression that I'm moving this line horizontally, but this is actually not true. If I add the input, I'm moving the line up and down, but the zero crossing moves horizontally, right? Okay. And now you can actually see the little square, the attractor there. Okay. Observe how the state variable tracks the input by relaxing to the new attractor, both in the trajectory plot and the phase plot. So, okay, so let's do this again. I'm moving to a new input. I'm moving back here. And let's look at this trajectory plot first. So I'm making a quite rapid change of the input. The green line is the input. The blue line is the activation itself over time, right? So here I drew the slider back down to the zero. So the input dropped to zero. And now what you can observe is that there's a very sharp decline of the activation, which will then level off. If I keep going, right? You can see there's very large decay, and then the decay kind of tapers off to the end. So this looks like an exponential decay, and it actually is one. And it does the same in the other direction. If I move it back up, you'll see very sharp increase, and then it tapers off again. Again, sharp decrease. Okay. You can observe the same thing here, only it's not as clear. You'll have to look at how fast the red dot is moving. Okay, so very fast, and then it gets slower and slower and slower. again, here, slowing down, slowing down, slowing down. So this is because the relaxation, the rate of change near the attractor is very small, right? You can read off the read off the values here. Around the attractor, they're smaller. Farther away from the attractor, they're very large. Okay, so if you're starting off far away from the attractor, you have a large rate of change, and the closer you get, the smaller the rate of changes, and this creates these exponential decay patterns that you see here. Okay, now the second task is called relaxation time. That's B. I'm going to read some of this again. Note how the state changes faster initially when the distance to the new attractor is larger. Oh, we just saw that. But the overall shape of the relaxation curve is always the same. And we also noticed that. Compare relaxation time for different times for different values of tau. We haven't done that yet. Use the parameters button, that was here, to set tau 2. So we'll have to move to node to U2 and change this tau value. Use the parameters button to set tau 2 to a value that is significantly different from the value of tau 1. To do this, okay, significantly different. Let's say tau 1 is actually also 20. So we'll set tau 2 to maybe 50 or 60, 3 times, and then click apply. And then it says use the same resting level same resting level. We have that here. It's both at -5. And non-zero stimulus. Stimulus is the input. So S1 and S2 are both 0. Then reset both activation variables to observe the difference in relaxation time. So is it running? Yes, it's running. Oh, sorry, no, I made a mistake. Non-zero stimulus, sorry. So we'll have to add stimulus. Let's put this to 8.8 and this to 8.8 as well. Okay, so and then reset both activation variables to observe the difference in relaxation time. So I'm doing a reset now. Both of them jump down and then they relax to the input. And you can already see, I'll do this again, that the activation of node 1 goes there much faster, right? This is still going and this has already been there. Faster, faster, and this is slower. You can also see here that this is moving slower. Again, it has the same shape, right? This is still an exponential increase, just like here, but it's stretched over time because it's slower. And this is because of the parameter. So if we look at this again, for node U1, for this one, we have a tau of 20. For node U2, we have 3 times that, 60. And this makes this this dynamical system much slower. You can also see the difference in the slope of this phase plot, right? This is steep, let's call this steep, and this is much less so, right? This means that the rate of change, even for things that are far away from the attractor, the rate of change is lower than here, for instance. Okay, now you can do this for different parameter settings on your own. I'm just going to go on to the next task. So the last task, task C of this first exercise, is called stability. I'm again going to read. Set the relaxation time parameters to very different values, for instance 10 and 1000. Okay, so we go to parameters. We set U1 to 10 click apply, you can see that this got very steep. And then we set node U2 to 1000. Apply. You can see that this got almost flat now. We remove, I'll read again. Add a small amount of noise to both systems. Okay, so that's the Q slider. Let's small amount, let's say 0.1. And observe how the activation variable with higher relaxation time, that was node 2, this one, deviates significantly further from the resting level and takes longer to return to it eventually. Use H as 0. Okay, we set H to 0 for both. And no input for both. And the noise should be the same for both. I already did that. Okay, now let's have a look at what is going on. Here you can see for this node, which has a fast relaxation time and this this downward slope, you can see that it's noisy, but it's noisy around 0. Right? It comes back to this again and again. Here you can see that it's noisy, but it's kind of drifting away, right? It should be around 0, but it's drifted up here, and it's not coming, I mean, it stays up here, right? This is because there is an attractor, but it's extremely weak. So it's not pulling the activation down here to the attractor as much as the noise is pushing it away. And there's another question: how is this effect reflected in the two-dimensional combined trajectory plot? So this is the plot down here, where you can see activation U2 and activation U2 and U1 at the same time. So we would expect that activation U1 here is around 0, and we can see that. But activation U2 is kind of drifting along this axis, right? And this is exactly what you're seeing. So we have a much larger variance around this axis than we have around here. And it gets even worse if we increase the noise to let's say to 0.2. You'll see much more drift then. Right, it moves up here, but again, mostly in the vertical. Okay, so this concludes the first exercise. Just go ahead and have a look at this on your own. Play around with the parameters and see that you really understand what each of these sliders do, what the contributions are in the equations. Look at the equations and have some fun just with the simulator. You'll understand it much better if you set yourself some tasks and try to figure out what it does on your own. Okay, so have some fun with this. I hope this video was useful, and yeah, enjoy.